conference, and the people who are the civilians, they all have red lanyards, so it's hard to distinguish who's who, unless you know him. So for those who are not with the conference, he's famous for many things, but among other things, he's also famous for what he's going to do now, is namely vulgarizing complex subjects such as was said famously by Anderson that more is different. So basically, if you have humans, if you have one person, if you just talk to one person, it's not the same if you talk to 100 or to a football stadium. The same goes for physics. And I think he will give us a good introduction to this, which is also basically the topic of the conference, which is more is different. So thank you.
Thank you very much. Can everyone hear me? Looks like it. Okay. Good evening. It's wonderful to be back in Montreal. I first came up here as a graduate student in an old car with a bunch of French guys about 40 years ago, and the city seems to have changed a little bit since those days. So I'm going to tell you about the strange new universe of quantum materials. This will be mainly an opportunity to revisit an amazing historical scientific event that took place 100 years ago, namely the discovery of modern quantum mechanics. And as you may know, across the world, at least across the world in physics, this has been the year to celebrate the International Year of Quantum Technology and Science. And that's because 100 years ago, 100 years and 1 month ago, a 23-year-old German student called Heisenberg took a summer vacation on the North Sea to the North Sea island of Helgoland, and he did this to get over his wretched hay fever, and when he came back, he returned with insights that literally shook the world of science to its core, precipitating the quantum revolution. And these are the cast of characters that were involved in the development of theoretical ideas associated with that revolution. So I'm going to tell you and give you a vignette of this quantum revolution. It's a non-expert introduction, at least, well, it's my version of a non-expert introduction. And it'll give me the chance to introduce you to these three wonderful characters, Heisenberg, Schrödinger, and Dirac, who together shared the 1933 Nobel Prize. I guess Heisenberg got the 32 prize, but they delayed it by 1 year, and so they all got the prize together. Okay, so, but I'm also going to talk about where we stand with quantum mechanics. It's a report from the halftime show, and I'm a solid state physicist, so I'll give you my perspective on it from the terrestrial standpoint. And last but not least, we're here in Montreal in 2025 at the Strongly Correlated Electron Symposium, where we all talk about quantum materials, and I'll try to connect up some of what I say with the vistas of this meeting. Okay. So let's go back to pre-Heisenberg and look at the very early part of the 20th century. And these three gentlemen really set the stage, analyzing a wealth of experimental data, which I will not go into, from the 19th century. And what did they do that shook the world? Well, they were really worried a bit about light. And in particular, why hot things change color. And Planck really studied this carefully, and he came to the conclusion that energy can only be added to the electromagnetic field in little bits. And Einstein took this idea and ran with it, and came to the conclusion that light is composed of particles, which we now call photons. This answered the enigma of why hot things change color, but it opened a Pandora's box of questions. Around the end of the 19th century, physicists were patting themselves on the back for having discovered radio waves, for finally understanding what light was, for understanding electromagnetism. And they knew it was made up of waves of electromagnetic fields. So what the heck was this new idea that it must be made of particles? How can electromagnetism be both wave and particle-like at the same time? Light, this is the force that surrounds us. How can it be made of waves and of particles at the same time? This was a great enigma, and because they didn't understand it, they gave it a name, and it was called wave-particle duality. And we're still struggling to this day with this concept. It's fair to say that we have the mathematics to describe this perfectly, but we're still in a process of converting that mathematics to a form of English that we can communicate in a non-expert fashion. So I want to introduce you to Niels Bohr. He's often referred to as the godfather of quantum physics, because not only did he provide some of the mathematics, he also was deeply involved in the philosophical viewpoint of what quantum mechanics was. What kind of guy was he? I don't know, I never met him, but let's look at someone who knew him intimately, what his thought was. And that person is Heisenberg himself. Here's Werner Heisenberg. And Heisenberg, like many physicists of the time, wrote and kept notes and wrote longhand about his ideas and who he saw. And this is what he wrote to a friend about Bohr. Okay? He says that for the first time I met Niels in Göttingen in the summer of I'm only 20 years old, in my 4th semester. People started young in those days. Okay? Full of light streaming in the open windows. He spoke softly and with some hesitation, but behind every carefully chosen word, one could discern a chain of thought which eventually faded somewhere in the background into a philosophical viewpoint which fascinated me. Bohr was a philosopher. He wasn't actually all that good at math. He used his mathematical brother to help him out a lot, but he really did think deeply about the meaning of the math he was using. Math is the language of theoretical physics, and often we can use it to calculate things, but translating it into words and philosophies takes a long time, and Bohr was a master of this. So what was he actually interested in? Well, he was fascinated by the sharp emission lines of atoms. 30 years of beautiful experimental work had led the physicists to know that atoms, when they emit radiation, don't just emit it as a continuous spectrum, but actually emit radiation as sharp spectral lines. And here you can see not very, very well the spectral lines. Well, it's on my thing here, but it's not coming up on the screen. Is it coming up there? Guys, the pointer isn't coming through. Never mind. Okay, well, I can't point on there. Tough luck. So here you can see these sharp spectral lines of hydrogen and sodium. Every atom has sharp spectral lines of this sort, and this was a mystery at the time. But Bohr felt he could use the ideas of Einstein and Planck, and he reasoned that if photons came out with discrete frequencies, then they must have discrete energies. And if they have discrete energies, the atoms must exist in states of discrete energy. And that meant that the difference in energy between those two discrete states had to be equal to h times the frequency. H here is Planck's constant. Okay? The transition from one level to another led to the emission of a photon of energy hf. This was an idea that Bohr put together in 1913, and he was able to actually reconstruct the energy levels of hydrogen, but something got in the way to further progress, and that something was the First World War. And so progress was somewhat slow over the next decade. Okay? He called these stationary states. So this was the early quantum physics. And this theory established many important new concepts: photons, stationary states, quantum numbers, and the mysterious wave-particle duality. These concepts would all feature in the new quantum mechanics. Why did you need new quantum mechanics? Because this was all ad hoc. It didn't fit in at all with the math of the time. It didn't fit in with classical mechanics. Okay? So we're now moving to the 1920s, the birth of the electron wave, and nothing comes without its social context. And the end of the First World War led to a time of terribly disruptive change in science, in art, and politics, and it's no surprise that in this disruptive environment, quantum mechanics was born. This is the spectrum of Ladenburg. It's a theoretical paper from 1922. They'd already worked out in great detail the spectrum of both helium and hydrogen, even though they had an ad hoc theory, and all of the quantum numbers had been labeled. Here is another revolution, Cubism, Picasso's Woman of 1924 from the Guggenheim Museum. If you make it out carefully, you can make out the reclining woman in this picture. And hyperinflation. If you're worried about inflation today, look at the inflation they had in the Weimar Republic. This is what would be called in those days a $5 billion note. In fact, today we'd call it a $5 trillion note. 5 times 10 to the 12 marks note that was published because of the hyperinflation. They didn't understand economics in those days. Perhaps we haven't learned too much. That was the situation. And it's against this backdrop that this young man, age 27, had a new idea. And from the perspective of today, it's surprising that no one had thought about this earlier. But what he reasoned was that electrons are waves, and it was a simple idea. It was the idea that, just like photons, electrons, if they're particles, must exhibit wave-particle duality. And by looking at the properties of photons, he could link the wavelength and the momentum, and his famous equation gave the wavelength of the wave in terms of the momentum of the particle. This simple equation links waves and particles. This simple equation is at the heart of wave-particle duality. But writing the equation doesn't mean you understand it. Right? His idea allowed the structure of the atom to be understood in terms of standing waves. In fact, this is a standing wave here. You can see its wavelength. And if you wrap a standing wave around a circumference, then you have to wrap an integer number of them. And that then describes the quantization, the selection of the stationary states that Bohr had discovered. And so it led to a breakthrough. He could understand what Bohr had done. And this discovery of his in 1924 was followed one remark. His thesis was reviewed by some of the great physicists and mathematicians of the time. Henri Cartan, Langevin, they all sat on his thesis committee, and they thought his work was excellent, but they thought it was a bit far-fetched. So they consulted the outside expert, who was Albert Einstein, and Albert said he's lifted the corner of a great veil. He would clearly regard it as the big breakthrough. Meanwhile, on the other side of the Atlantic, on this side of the Atlantic, down at Bell Labs in the heart of Manhattan, in fact, you can visit the very location where this discovery was made, because it's just off the High Line. It's labeled there by the AIP. And what have these guys done? Well, they'd actually discovered that electrons behave like waves. And what does that mean? Well, waves have the property that they superimpose. Here is a wave coming out of a slit, but if you now take two waves out of two slits, then you'll notice that they constructively interfere in certain directions. This is called diffraction. And Davison and Germer did an experiment with a cathode ray tube, and it happens that they made a mistake and someone cracked the tube. They had to re-anneal the nickel, and when they did so, it became more ordered, and lo and behold, they saw this wonderful pattern of diffraction of electrons. And later on, when they heard about de Broglie's theory, they were able to show that given the energy of the electrons, 50 degrees was exactly the right angle for diffraction. So this event took place in 1924. De Broglie never followed up with a wave equation. He didn't quite know what the waves were. He thought they might pilot the electrons. In other words, he wasn't ready for the full leap that an electron is actually a wave. And what kind of new mechanics was needed? These were open questions in 1924. And these questions helped to precipitate the revolution. And so between 1925 and 1933, Heisenberg, Born, Jordan, Dirac, Pauli, and Schrödinger, together with several others, went on to formulate the mathematical framework of quantum mechanics. And so I will tell you a little bit about this in a non-mathematical language. It's somewhat challenging, but I'll do my best, okay? So this was the leap. And here's the man who precipitated it, Werner Heisenberg. And he was a new postdoc with Max Born. He was 23 years old, meaning he was born in the 20th century. And he had intense hay fever. He was apparently a great athlete, but he was subject to a lot of hay fever, so he went off to Helgoland in the North Sea where there were no flowers. And as the legend goes, he pranced around on the cliffs trying to figure out how to make the new mechanics of quantum physics. And he came back with radical insights into the quantum world. 1 month ago, there was apparently a big party of a whole bunch of nerds on Helgoland celebrating this great event. When he came back in July, pretty much 100 years ago, he wrote to his friend Pauli, and he said, well, all my wretched efforts are devoted to killing the concept of orbits completely, which cannot be observed anyway. You may recall that classical mechanics treated the atom as a kind of solar system. And so that meant, how would you select the orbits? And he realized that you could never observe an orbit. We now know they don't actually exist, although we use the word orbital. And so he wanted to take another approach, okay? And this was the paper that he submitted to Zeitschrift für Physik in 1925 at the end of July. So what did he do? It's actually a wonderful paper. It's a phenomenological paper. It is not the foundation of quantum mechanics. It's the foundation of the mathematical ideas of quantum mechanics. And he basically put together a number of very simplifying ideas. The first thing was, he didn't try to treat the entire atom, the hydrogen atom. He used the idea that we still use today, that an atom, when it emits radiation, is basically an oscillator. So he wanted to study an oscillator. And so that he did, but the key innovation was that the frequency of the light coming off wasn't, as in a classical oscillator, the frequency of the oscillator, but instead was the difference in energy between the two states from which the photon was being emitted, okay? And the second thing he did was to realize that the amplitude of displacement depended on the particular transition. And so instead of having one amplitude, there had to be one for each transition from the initial state to the final state. And so he had to replace the displacement of this poor oscillator by a table of variables oscillating at these frequencies. So he wrote this equation down, and I reproduced it in its Gothic form. And in so doing, what had he done? Well, he realized that this meant that replacing x by a table, a matrix, meant that x times y is not equal to y times x. And he later learned, when he told his advisor about what he'd been doing, his advisor Born, that this is a matrix. And this was then the origin of the term matrix mechanics. This is what he wrote to, when he got back at the end of his paper, whether a method of determination of quantum theoretical data from relations between observable quantities like the one that was proposed here can already be regarded as satisfactory in principle, or whether the method represents only one more much too bold attack on the problem of formulating a quantum theoretical mechanics, will first be clarified by deeper mathematical examination of the method that was employed very superficially here. How I wish we could write papers like that today. Okay? Even though it was the big breakthrough, he was very tentative about it, he was very worried about it, and he almost didn't submit it for publication. Okay? We could learn a lot from our antecedents. And it led to an earthquake of activity, because although it didn't provide the equations of quantum mechanics, it suggested the way forward very clearly for those who knew matrices. These were two gentlemen who worked fervently over the summer, and by the 27th of September, they'd submitted their paper on quantum mechanics. It was the first paper to introduce physicists to matrices. In fact, the first 10 pages are entirely about matrices. How to use them, how to take functions of them, how to invert them, although curiously, they didn't know about eigenvalues. They're not mentioned, eigenfunctions, they're not mentioned anywhere in the paper at all. Everything is entirely with matrices. Here's another person who got on in on the act very early. This is a graduate student at Cambridge. Heisenberg went to Cambridge to give a talk. He didn't talk about quantum mechanics at all that summer, but he left a preprint with Dirac's advisor, who didn't understand a word of it, but he shoved it off to his student and said, "Hey, here, Paul, why don't you go and take a look at this? It looks sort of interesting." And so Dirac spent the entire summer also studying Heisenberg's paper, and probably just as he was sending off his paper, he received the preprint from Born and Jordan. It must have been very frustrating for him, because he thought he'd made a great breakthrough and he'd got the German preprint in his hands. Too bad. Later, on the 17th of July, Pauli actually worked out the hydrogen atom entirely using this new quantum mechanics. Unbeknownst to him, someone else was doing it at the same time using a completely different method. So this is where we were at the end of 1925, okay? This man took a different path. You'll see that the Heisenberg approach didn't pay any reference to de Broglie's work. And Schrödinger picked up that alternate thread. It's rather interesting to speculate that had Heisenberg not done his work, that Schrödinger might have gotten going anyway. We don't really know. He was certainly stimulated by the Heisenberg work. He said he was repelled by it. He was repelled by the Göttingen approach to quantum mechanics. It didn't fit in with his way of doing things at all. So here's the backstory to his discovery. So he was at Zurich, University of Zurich, and he gave a colloquium on de Broglie's thesis in December of 1925. And according to the urban legend, physics colloquia haven't changed at all. Physicists are just as impolite as they are today as they were in the days gone by. Peter Debye said to Schrödinger, "You aren't doing anything important these days, why don't you see if there's a wave equation?" or something like that. We don't actually know what he actually said on the day, but Peter Debye had studied under Sommerfeld, and he knew about wave equations, and he was really surprised that de Broglie hadn't done this. The more surprising question is why he himself didn't go to work out the wave equation, but he didn't. So this is where the breakthrough of wave mechanics took place. Schrödinger went to Arosa with an unknown Mithras in Christmas, New Year of 1925, and he worked fervently. And this is a page from his notebook, which contains the first known rendition of Schrödinger's equation. You can just about make it out on the third line there. He was trying to work out the solution to these wave equations. And this is the form in which he wrote it down. He then went out and worked out the spectrum of the hydrogen atom. Okay? And on the 27th of January 1926, Schrödinger published this first paper, Quantization as an Eigenvalue Problem. Oh, that's interesting. Back again. And the important part about this is that the orbit was now completely replaced by an electron cloud. And Schrödinger had 6 months of intense activity, which really rocked the world because his approach was much more accessible to the world of physics than the matrix mechanics approach was at the time. And so the first paper came out in January. There was 2, there was 3, there was 4. And these 4 basically are the culmination of all his life's work. So in the second or the third, he already had solved the equation and looked at wave packets. In the fourth, he had worked out the time dependence. He then, in March, wrote a paper in which he figured out the equivalence between the matrix mechanics and the wave mechanics approach. And in particular, this one equation here shows how he worked out the matrix element of an operator between the states L and M, G super Ln. And in his fourth paper, he also worked out the many-particle Schrödinger equation. He is shown for 2 particles. And finally, for the English-speaking audience, he published a summary of all of this in a review article in the Physical Review in December of 1926. It was the first English paper on wave mechanics, English written paper. Beautiful review. So, one thing wasn't at all clear, and that was the meaning of psi, the meaning of psi squared also, okay? The electron is everywhere in the Schrödinger approach. So what does psi mean? Schrödinger favored interpreting it just in terms of a charge density, a kind of pilot wave for the particles, okay? But Max Born thought physically, his advisor, and he realized that it wasn't consistent with the fact that when you scatter electrons, they go click, click, click into your Geiger counter. And he was probably the first to really think about the paradox of electrons diffracting, but also coming into a specific detector. And so he then deduced that this meant that the number coming through was proportional to a probability, which was psi squared. Born received the Nobel Prize for his work on quantum mechanics not until after the Second World War. He was one of the last folks to receive a Nobel on this subject. Okay, but what does psi mean? We're still struggling to this day about what is the wave function. It represents the uncertainty as a wave. It's not really a probability wave because it carries a phase. It's something weird. And later, Heisenberg helped to wrap this up with his uncertainty principle in March 1927, which tells us that we cannot simultaneously measure the position and momentum to arbitrary accuracy. So by the year 1927, basically all of the math of quantum mechanics was worked out. Most of it, anyway. Here you can see the old school in the photo, Marie Curie, Lorentz, Einstein, Planck, and Bohr, and then the young types are all lined up next to each other, more or less, over here. You can imagine that they had wandered over to the photograph and they were talking to each other about their ideas or arguing. So the mathematical foundation was largely complete with a very important codicil. And what was that codicil? Well, I want to end talking about this bit about how antimatter and LEDs are linked. Many of the lights in this room are LEDs, and they work on a principle which has its origins in the next phase of quantum mechanics. And of course, this was combining quantum mechanics with relativity. Einstein had established the laws of relativity, but Schrödinger's equation only worked for non-relativistic electrons. So what's to be done? In fact, Schrödinger himself had tried many times to produce a relativistic equation and given it up because it had certain in fact, it predicted energy levels that weren't consistent with measurements. Okay, and so from relativity, there's a curious relationship between momentum, mass, and energy, which is a kind of Pythagorean triad, with the horizontal being the rest mass energy, the vertical being the momentum, and the square root of the two gives you the total energy. This then poses a problem to any wave equation, because how can you take the square root of a wave equation? A wave equation isn't the thing that naturally has a square root, because it's a linear object. So how do you do it? Well, one way forward was just to make a wave equation for E squared, okay? But this man, Paul Dirac, finally caught up with the rest of the crowd and overtook them. And he found a way of taking the square root of a wave equation. And the way he did it was to use a matrix version of a wave equation. And here it is. This is one of the few equations of physics which can be found in Westminster Abbey. Here it is inscribed there. Some people say it's rather apt that Dirac has two stones memorializing him, one in Florida and one in England. It's a little bit quantum mechanical to be, in some sense, buried in both places. So he was a fascinating fellow, and this equation did some things right. It predicted the right dispersion of electrons with an energy E equals mc squared, but it did something that was amazing. It predicted something that had been identified on phenomenological grounds, namely that electrons have spin. And we call it spin, but it's not really like any spinning object we really know, because an electron can only have two states of spin, up or down. And this equation predicted that, okay? But it had another property, that when you solved it, a result of having taken the square root was that there were two solutions, plus mc squared and minus mc squared. And although everyone thought this was a beautiful piece of mathematics, the general view in the physics community was that this spelled doom for Dirac's ingenious equation. He'd never escape this. This was the end of it all for him. And so it took a while, unlike Schrödinger's equation, for his equation to catch on. Okay. And during that time, he thought a lot about this, and the first thing he did was propose a beautiful explanation of how to deal with the negative energy states, and that was, well, fill them up with electrons. Okay, this is what he called the filled C, and once the C was filled, of course, you have to wonder how you get an infinite number of electrons to fill an infinite C, but if you just don't worry about that, and it could be dealt with by changing the math a little bit, it then meant that if you made a hole in that filled C, that hole would now be positively charged. It's like a balloon. A balloon filled with helium behaves like a negative mass particle, while a hole in a negative C behaves like a positive charged particle. And so this was a nice way out of things. And for many years, Dirac thought the hole was a proton. That's what he wrote in his paper. He was at this stage not a fully transformed theoretical physicist. He didn't take his equations at face value. He thought, well, I've got to look for the particle that fits my equations, and that particle, at least with the proton, even though its mass was 2,000 times too big. And these two characters persuaded him he was making a mistake. And it's rather interesting that the future director of the Manhattan Project played a seminal role in the discovery of antimatter. In fact, it's interesting to read his paper. Does anyone know what he did? Well, he said, okay, I believe Dirac. Let's look at the hydrogen atom, which has a proton in the middle. Let's calculate the lifetime of the hydrogen atom. And it came out to be 10 to the minus 15 seconds. And there went that idea. And so he, along with Weil, who was the great mathematician of quantum mechanics at the time, persuaded Dirac that in fact they must take his theory literally, and that the hole in the electron C is not a proton, it must have the same mass as the electron, it must be the electron antiparticle. And Dirac changed his heart in 1931, just 6 months before the observation of the positron. In fact, had various experimentalists looked at their data carefully, they would have discovered the positron before Dirac made his prediction, because many people had seen the curved tracks curving in the wrong direction in Paris and in England, but they had hesitated to make the assertion that what they were seeing were positively charged electrons. And so it took the guys in Pasadena to make this assertion. They didn't know about Dirac's theory, but he was just there in time, and this meant he got his name on a Nobel ticket. But there's something interesting about this whole model here. Not only does it describe the vacuum, but it's also fundamental to our modern understanding of insulators and semiconductors. And in particular, an LED light works by electron-hole annihilation. And when that happens, it sends out a photon, a blue photon if you have the right stuff, the right semiconductor, but green and red are also possible. And so it's rather interesting that this theory of the vacuum also proved to be something very useful in condensed matter physics, and the word hole, which preceded the word positron, stuck in semiconductor physics. So there were many early triumphs of quantum mechanics, and I've added superconductivity there, but from the 100-year mark it was an early triumph, but it took actually 40-odd years before that problem was solved. But the periodic table and all of chemistry, the hardness of matter, magnetism, antimatter and semiconductors, superconductivity all came out of this. But if you're a hard-nosed bureaucrat, this was not the triumph. The triumph was the impact on technology, because from understanding comes the ability to apply your understanding. And the semiconductor industry with Moore's law, lasers, LEDs, neodymium magnets, electric vehicles, wind turbines, and not long into the future, compact tokamaks are all examples of the technology coming out of this great advance. In fact, according to some counts, 30% of the US economy depends on quantum mechanics. This is a stupid number because, of course, everything depends on quantum mechanics. You could easily say 100%, but never mind. Okay, in my last part of time, I want to speculate 100 years on, could our understanding of the quantum world be incomplete? And by that, I mean not just a little bit incomplete, not just a correction, not just the addition of a particle or a Lagrangian, but could it be incomplete in a major way? Okay. And that affects the condensed matter world because we know that from Newtonian times that what works in the lab works in the cosmos. And since the Renaissance, most of our scientific era has been classical. Quantum mechanics has only been the last 100 years. I put Feynman somewhere in the middle of that. The quantum era has, from this perspective, only just begun. Okay? And we know already that what goes on in the lab affects the cosmos. Anderson's understanding of levitation of superconductors led to a deep insight into the standard model, now known as the Anderson-Higgs mechanism. Okay? And so, from the apple to the levitated superconductor, the amazing thing about nature is that the principles we learn in the lab teach us about the cosmos and vice versa. And this is a principle that is as alive today as it was in Newton's time, and it provides a very powerful motivation for research into quantum materials. Let me talk a bit about that. So here we are at SCES in Montreal in 2025. Strongly correlated electromaterials would now probably be translated as quantum materials. What are quantum materials? Well, this is what is a material. Iron nails is a nice example of a material. Here's a crystal lattice of iron, and here's an iron atom, although not the way we really should draw it. This is just drawn schematically. And so here's how we understand a material, but a quantum material really refers to the combination of electrons, which are waves, inside a lattice perhaps. According to Wikipedia, quantum materials is an umbrella term in condensed matter physics that encompasses all materials whose essential properties cannot be described in terms of semi-classical particles and low-level quantum mechanics. Well, that's a very large swash of them. Here's another one. Bob Carver, I will not endeavour to provide a precise definition of a quantum material. I know when I see it. But my definition is that it's a miniature quantum universe. And there's very good ground for thinking this. If we go to the periodic table, we know that when we combine elements, A plus B does not equal C because of interference. We call this emergence, and each new compound is its own multiverse. And I say this with a bit of tongue-in-cheek, but it's also true. Okay? And one man who really pushed these ideas into the modern context, and we heard this in the introduction, Phil Anderson, whose name is not there for some reason, mentioned that the behavior of large and complex aggregations of elementary particles is not to be understood in terms of simple extrapolation of the properties of a few, and at each level of complexity entirely new properties appear. This was from his seminal article, More is Different, from 1967. Well, that could almost be a time that I should stop, but let me continue a little bit longer. Let's see how far we get. So this means that as we explore the periodic table, we discover amazing things, such as this elemental 2D metal twisted bilayer graphene, or IPCO high TC superconductors. And as we explore the periodic table, we're really in a time that perhaps could be compared with the days when the ships set off from Europe to explore the Atlantic, because the periodic table really is a new tract of territory that we've only touched. And as we go from the elements to the binary, to the tertiary, to the quaternary, the number of possible compounds exponentiates in a way that we can only touch upon. And there are strange behaviors going on. This is the resistivity of a cuprate superconductor in its normal state, and out of desperation, our field has referred to them as strange metals, not because they have something to do with strange quarks, but because we just don't understand them. You'll hear a few talks about this at this workshop, this meeting, and one of the key defining features of one class of strange metals is that they have a linear resistivity, which if you plug into the world's oldest theory of the metal, namely Drude transport theory, you conclude that the scattering rate is determined by Planck's constant and the thermal temperature. It's called Planckian scattering. Here's another problem that we don't understand, the problem of quantum phase transitions. And quantum phase transitions involve a point of transformation between the two multiverses. It's a phase transition driven by an instability of the quantum ground state and determined by Heisenberg's uncertainty principle. We don't... Okay, and another idea that I wanted to mention is the idea of phase coherence. It's fundamental to a wave that it has a phase, and you can sometimes synchronize different clocks, and in this case different waves, all to have the same synchrony, the same phase. And the idea of coherence has its origins in the work of Bose and Einstein, actually dating back to 1924-25. And Einstein extended Bose's works and argued that one class of particle, the boson, when cooled down, would coherently superpose into a Bose-Einstein condensate. When this happens, the wave packets all line up into a coherent state. This condensation leads to macroscopic properties, a macroscopic quantum wave function in which the phase is coherent and rigid. And this describes lasers. This describes superfluids, and it describes superconductors, in which different types of bosons coherently condense into a macroscopic quantum state. We're fascinated by these phenomena. High-temperature superconductors involve the formation of Cooper pairs, but they're somewhat different. In a regular superconductor, Cooper pairs are formed by a glue, giving rise to an energy gap. This glue is phonons in a regular superconductor, and this leads to supercurrents that flow persistently without resistance, leading to magnetic levitation. I think I'm in question time now. Okay. So anyway, these are the TCs versus time, and of course high TC has taken us to much higher temperatures and to phenomena that require only liquid nitrogen for their cooling. The ITC involves a different kind of gap, a D-wave energy gap with nodes. Okay, and so we're fascinated by these phenomena. We're fascinated because they undoubtedly have important applications, and we're worried about how we might find new superconductors. What new kinds of electron coherence and what new kinds of quantum material are possible? What are the present and future applications of superconductors? We can also ask. Well, these are various little pictures here. One is transmission lines. The other that you would know if you'd had an MRI is that they can look inside your body using these intense magnetic fields. And in fact, this uses the old niobium technology. Every single MRI in the world at the moment is cooled using helium, but the new generation may be cooled using nitrogen. And this is the one that's captured a lot of imagination recently. The energy density inside a tokamak goes like the fifth power of the magnetic field. So if you can rack up the magnetic field, you can get a much more compact tokamak. And there are something like 30 companies around the world trying to make tokamaks or nuclear fusion devices using superconductor tapes. And these tapes have made tremendous advances, but we'd still like to push them to higher TC or higher magnetic field, and there's tremendous scope there. Well, I just want to end with a remark that connects up with William's thoughts in the last talk, that information is physical. And this is one of the issues that we're facing today. We don't understand the connection of quantum mechanics and information. And it's important not only for quantum materials, but it's also important, hey, there's no one after me, so I can go on a little bit longer, come on. So it's also important because we'd like to understand information from a quantum mechanical perspective. The fiber optic carries classical information, but in the new world, we'll presumably be transforming and transmitting quantum information. And today's theories of quantum information use entanglement as a proxy for information, and it's an evolving story, a broad horizon that stretches from quantum cryptography to black holes to quantum materials. And last but not least, I think it's really important, and I haven't touched on it, to think about the fact that the impact on quantum mechanics in our world may stretch beyond the current Copenhagen interpretation. And just a few moments on this thought. So one of the key elements of quantum mechanics is the notion of wave function collapse. It's an idea which we adopt without much thinking, and it has a number of strange alternatives. But the basic idea is that if we look at an electron inside an atom, we collapse it to a given position, an eigenstate of position, okay? And that process is not governed by the unitary evolution, by Schrödinger's equation. My namesake, Piers Coleman, has thought a lot about this when he was alive, and he argued that you don't need wave function collapse. And here's a quote from a marvelous paper entitled Quantum Mechanics in Your Face, which actually probably a non-expert could read. And now people say the reduction of the wave packet occurs because it looks like the reduction of the wave packet, and that is indeed true. But what I'm asking you in the second part of this lecture to consider seriously is what would it look like if it were the other way around, if all that ever happened was the causal evolution according to quantum mechanics? It's, unfortunately, Sidney Coleman is no longer with us. I would love to have a discussion with him. Because, of course, what that means, if you take it literally, is that as that atom evolves, and we observe it, then the information about that observation ultimately goes into our brain. And so that means that when you observe the world around you, your brain is becoming entangled with the electrons in the vacuum around you. And that's all very nice. That means that you're in a, you are in an entangled state with the world around you. Very good, okay? But there is a principle that goes back to the very beginning of philosophy, the beginning of the Renaissance world, which is the Cartesian principle due to René Descartes, which is, in the modern version, it's cogito ergo sum, I observe, therefore I am. And of course, it means that the singularity that each of us witnesses and we use as the basic model for our understanding the world around us is starkly different to Coleman's unitary universe. Literally, then everything we're seeing just appears to be a single quantum universe rather than actually being so. And so this raises the fascinating question of the connection of quantum mechanics with observation and ultimately, although it's a dangerous territory, the notion of consciousness. And one physicist has actually been actively pursuing an interest in this, and he's been asking, do nuclear quantum spins play a role in brain operation? Now you might say, well, what's gotten them into that? And it's simply because it turns out that lithium-6, which has a very long nuclear decoherence time, is the active ingredient in lithium bipolarity drugs. You take lithium oxide if you're bipolar, and it actually works. And no one understands why. Lithium-7 has never been properly tested on humans, but when tested on rats, they find that lithium-6 leads to rat completely children. So clearly the different isotopes have a big effect, and you can't account for it in the different isotopic mass because they have the same diffusion time. And so this has led some to consider the possibility of a quantum brain, which would mean that the brain has actually evolved to actually take advantage of entanglement in some way. And presumably, if this were true, according to Fisher, this would involve the phosphorus nuclei in the brain, which have very long decoherence times and perhaps are interfered by the lithium. So, were this to occur, perhaps some point in the second half of the quantum revolution, this will mean there will be a collision between measurement and quantum information theory. If that collision actually takes place, then it would be a Copernican moment in the evolution of our understanding of the world around us, because quantum mechanics applies to everything and the brain isn't excluded from that consideration. So that's my talk. These are the conclusions. A quantum revolution was an earthquake in conceptual and mathematical of the world, and it reverberates today. We're only likely halfway through the revolution. I didn't have time to tell you how long it took for the classical revolution to go forward, but at the 100-year mark, it was still woefully incomplete. Quantum materials will transform the 21st century, and I've got a picture here of a compact tokamak with a high TC magnet. And quantum information and measurement theory are likely to take quantum mechanics beyond the Copenhagen interpretation in the second half of the quantum revolution. Thank you very much.
Who has questions?
I think there's about one member of the audience who's not a physicist.
Okay, so since this is a talk about the general public talk, maybe so I can have some philosophical questions regarding your beautiful talk. Yeah. So as far as a simple physicist is concerned, we are still fighting about this on a philosophical level about the predictive theories, right? So from the strongly coordinate electron systems established theorists, what do you think about our predictive power? About describing our world. in a quantum universe in a sense, for example? Are we very much successful there, or?
Well, I would say that we're very much in a phenomenological mode of operation, or should I say Baconian approach to science. In the study of quantum materials, we are far from the point where we can predict in great detail, except in areas where we understand the physics very well. For example, the properties of ferroelectrics. These are accessible to ab initio theory, but the properties of oxides and magnets, they are still over the edge, and predicting what the known unknowns is beyond our capability. As you exponentiate outwardly, you eventually reach non-equilibrium matter and biological matter, and as far as we know, there's no point at which quantum mechanics ends. And so from that perspective, we're very, very far from having a complete understanding of emergent quantum matter. And the role of quantum materials is that they are at the simplest end of that spectrum. Okay? We at least understand the basic principles. We know what equilibrium quantum matter looks like, and even that challenges us, and even that gives us exciting new technologies. So I would say that to some extent the theoretical community doesn't realize where it is. It doesn't appreciate that it's not in an ab initio mode, and that it needs to be a little bit more humble, as I showed you Mr. Heisenberg himself was. I think we need to stick a little bit more closely to phenomenology and use that to build small theories that will lead to bigger theories. And that's one example of that, which is very much on my mind, is the strange metal. I don't think it's ready for top-down theoretical treatment. I think we need to start with the phenomenology first.
Hi, thank you. So if I understood correctly, this last part, it means that Boltzmann brains are not so strange predictions of how we understand the universe, right?
Sorry, you said Boltzmann brains are not...
So this is this strange theory that in the infiniteness of the universe, at some point, a brain can pop out of the vacuum, and could be us or not, and in the infinite time of the universe, there will be more brains than people that ever existed on Earth.
Well, presumably, at the Big Bang, everything was not sentient. So sometime between then and now, sentient life has evolved. So that seems to make sense, but on the basis of, I think you are living proof of this, are you not?
Yeah, the strange theory is that
yes.
Everything could be just a memory of this brain that spotted for a microsecond and then collapses immediately after.
Okay, I don't know. I have no comment. But keep the questions going, they're good ones.
Wandered in off the street. I was kind of interested in just the bit what you were talking about at the end regarding the kind of connection with consciousness, because I think one of the things my profession kind of struggles with is this idea of determinism, and that, you know, theoretically everything is determined, and so where does free will and consciousness kind of fit into the kind of physical model of the universe? And, you know, I'm just interested in the idea that the kind of quantum mechanics has something to say about that, and something to say about how, you know, how do we escape the kind of idea that how things are in the future are predicted by how things are in the past, and there's no space for consciousness and free will, and does quantum mechanics give us any hope that there is some free will available in the world?
Thank you for that question. I'm much less qualified than others to comment on this. I do know, however, that when I start talking to some of my biology friends and start saying, well, couldn't the brain be quantum mechanical, they get very angry. It's one of their immediate response, which is partly because they don't regard a physicist as qualified to even talk about this. However, I should have had a biography here, and one of the things that I would direct you to is Schrödinger's book, What is Life? Because he thought very carefully about how quantum mechanics might affect free will, and has many thoughts on it. And it really has bearing on fundamentally on what measurement actually is. And if you don't know what measurement is, you don't really know how to comment on that. I mean, if I let me just try to put this from perspective. If I look at you, I don't actually know that you are sentient. I know that you are a biological robot. And so from my perspective, the quantum mechanics is evolving smoothly inside you. And but that doesn't necessarily mean that you're deterministic, because quantum mechanics evolving means that okay, you're maybe following a path that's somewhat close to the deterministic path, but fluctuations around it. And so there is a lot of room there for free will that doesn't exist in the classical picture. But whether that free will is driven by thermal noise and the fact that you're at room temperature, or whether there's any room inside that for coherent quantum mechanics is a matter of huge debate. And that's why Matthew Fisher has focused on the nucleus as being a possible area, because the coherence times of certain nuclei in the brain at room temperature are minutes. So it's a curious number which corresponds to the timescale of short-term memory. Yeah, this gentleman needs the mic.
The Copenhagen interpretation of the wave function, the collapse, is a way to introduce form in nature. Because if you look at the most basic constituents of matter, there are point particles like electrons, quarks. How can you generate form out of the formless? So this is a response to this is the collapse of the wave function. Because you take, for example, an electron in the hydrogen atom ground state. If you make one measurement of the position, you find 1 point. But if you make 1 million, you reconstruct the spherical shape. So this creates the notion of the spherical shape. So I think the Copenhagen interpretation is correct in the sense that otherwise we could not describe form in nature. How do you like this observation?
I'm going to say no comment, because I think it doesn't affect the approach that I take and I tell my students to take, which is shut up and calculate. So the rest is philosophy, and although I would comment that there's a lot of interest in measurement-induced phase transitions nowadays. And presumably, if you did measure a hydrogen atom repeatedly, you would knock the electron to all hell. It would be ionized. And so you couldn't actually do what you just stated. If you tried to... Yeah. Okay, I think it's the point where we need to descend to the bar. Ascend to the bar, yes, okay, great. Thank you, everyone.
So cocktail is upstairs.